This video is the first video in a series on Lesson 6, Hydraulics of Networks, and specific mathematics involved in network simulation models. At the conclusion of this, we'll solve some simple networks using Excel as the computation engine, using the same algorithm that's embedded into commercial software. And then we'll move to commercial software for practical application. The point of understanding what's going on under the hood is sometimes you get results that don't make sense, and it might be that you've set up the problem wrong, and this is a quick way to find out. So we'll examine network hydraulic principles, and we'll construct a network system of equations. We'll do this by example, and then finally we'll add pumps. This is going to be multiple videos, so this one will end, and the next one will pick up at the next logical section. The hydraulic principles there's two principles that we involve in steady flow network simulation analysis. The first is conservation of mass at a junction. It says that the sum of the inflows minus the sum of the outflows equals 0 at a node. Positive demand at a node is an outflow. Negative demand is an inflow. And there's one balance equation for each node. The head at a node has a single value, meaning that two different values of head can't exist simultaneously at a node. Often expressed as a pressure, and you can visualize that as the height of a column of water in a piezometer above the junction, and then relative to whatever the measurement datum is, that gives total head. The other principle we use is head loss along a pipeline. We have conservation of energy along a conduit, which employs the modified Bernoulli's equation, and essentially what we have is total head at one node minus the head loss in the path going from that node to the next node equals total head at the next node. So there'll be one energy equation or one loss equation for each link. Each link is going to only join two nodes, and that information, the flow balance at the node and the head loss terms along the links, are contained in something that I'll refer to as a node arc incidence matrix. So let's look at a simple case that will allow us to construct some of these ideas and develop an algorithmic approach to solving network problems. We're going to use a branch system. It's not a network in the usual sense in that it doesn't have closed loops, but it's a good starting point. If we write the various head losses in each pipe, we could come up with the expression that the total head at A minus the head loss from A to D, which is this term, equals the total head at D. Total head at B minus the head loss from B to D equals total head at D. And then total head at D minus the head loss from D to C equals the total head at C. They're rearranged a little differently here in the diagram, but that's essentially what those three equations are. And then continuity at the node gives us a closure equation that says that the inflows minus the outflows equals 0. The rose-colored terms are unknowns. There's three rose-colored terms, and then the green terms, which is the total head at node D, is the fourth unknown. So we have four equations and four unknowns. It's nonlinear because of the squared velocity term, and so we would find something like a Newton-Raphson quasi-linearization technique quite useful. And because it's quadratic, we can find answers relatively quickly. So let's take a brief tangent here and remember or refresh our memory of quasi-linearization Newton-Raphson techniques. Back in our introductory engineering mathematics classes, or whatever it was called for you, MATLAB class, we were introduced to Newton's method. And Newton's method is a tool that allows us to find estimates to solutions of equations that come in forms that are not easily solved by algebra. And in these cases, a numerical method is required. So Newton's method starts with, let's write our problem in the form of f of x equals 0, and then by successively manipulating guesses for x, we'll find values of x until the function evaluates close enough for 0 for us to accept. So let's look at this graph here. Let's suppose here's our function x, and the root we're looking for is over here, but we don't know where it is yet, and we make an initial guess, x1. We can evaluate the value of the function at x1. That's pretty easy. We can find the slope of the tangent line, because that's simply the first derivative of the function at x1. We can project that tangent line back to the f of x equals 0 axis, and where it intersects is our next guess, x2. We evaluate the function at x2, repeat the procedure, and it projects back to x3. We evaluate at x3, repeat the procedure, and we would probably get pretty close to the root in this drawing. So the formula for x2 can be derived from the geometry of that triangle, x2, f of x1, and x1. From the geometry of the triangle, in the definition of a tangent, we have the tangent of that angle is df dx evaluated at x1, which is equal to f at x1 divided by x1 minus x2. We'll solve that equation for x2, and we come up with a formula that expresses x2 in terms of the first guess plus a correction term. So x2 is equal to x1 minus f of x1 divided by df dx evaluated at x1. Once x2 is calculated, we can repeat formula 14 and do it iteratively until we get one of three outcomes. We actually get the root we're after. The thing diverges to plus or minus infinity. When that happens, it does it quickly, and it's quite dramatic. Or we get a thing called cycling, where it hovers around. You get a series of xk, xk plus 1, xk plus 2, and they keep repeating themselves. The generalized formula is xk plus 1 equals xk, where k represents the iteration count, minus f of xk over df dx at xk. If the derivative is evaluated using analytical derivatives, it's called Newton's method. If we use numerical derivatives, it's called a Quasi-Newton method. Here's an example using analytical derivatives. I'll go through it pretty fast, but we can discuss the algorithm really quickly. Put the function in the form, code it into a computer. Put the derivative in proper form, code it into a computer. Make an initial guess of the solution. 0 and 1 are usually pretty convenient. 0 or 1. Evaluate the function, evaluate the derivative, calculate the ratio. Subtract the ratio from the current guess, save the result as the update. Test for stopping. Did the update stay the same? If yes, then stop. You either have a solution or you're not going anywhere anyway. Is the function nearly 0? Yes, stop. We have a solution. Have we tried too many times? Yes, stop. The process is probably cycling. We're not going to get there. If stopping is indicated, proceed to the next step. Otherwise, go back to step 4 and keep repeating. When we get to stopping indicated, report the last update, related information, and we're done. So here's an example. Suppose we want to find the root of f of x equals e to the x minus 10 cosine x minus 100. So we need to code the function into a script. In this case, it's using R, but you can do this in Excel. We need to code the first derivative into a script. And then we need to get an initial guess of how many iterations, stopping tolerance. And finally, Newton's method isn't very long. We start the iterations, and this line right here calculates the update, and then these lines test for whether there's stopping. Okay, we don't have to necessarily use analytical derivatives. They can be replaced by approximations, and that's a quasi-Newton method. And in this equation 18 in this diagram, or in this document, is showing the case where first order finite difference is used. All right, so that we could even get really fancy and code it up like that, because it can be done with alternate guesses of the function. That's for one-dimensional cases. Once we move up to higher dimensions, things get a little trickier. So things that cause the methods to fail, multiple roots, and so we have sensitive dependence on initial conditions. Depending on where the guess is, it will either converge to this root or that root. Cycling is where the result of the tangent is such that it just cycles around a root. The usual solution to that is to put a a random bump in the answer and keep going. And if we get near zero derivatives when everything else is non-zero, we'll start dividing by zero and we get plus or minus infinity and the numerical method falls apart. So that was Newton's method in one dimension. Now let's go up to higher dimension cases, which are, okay, looks like I just saw them. Okay, so now we're going to go into higher dimensions. And so this particular portion of the document shows nonlinear systems by a Quasi-Newton method. And our function is now a vectored value function of a vector argument. And we'll see where that comes into play in a minute with pipelines. So the f1 function is x squared plus y squared minus 4. The second function is e to the x plus y minus 1. Recall Newton's method for scalar valued functions. We need something to replace the df dx term that can deal with vectored value functions of vector arguments. And then the rest, everything else can be treated as a vector or a matrix and it will just work. So the equivalent of the df dx term is the first partial of the function with respect to the first variable, the partial of the first function with respect to the first variable, the partial of the first function with respect to the second variable, the partial of the second function with respect to the first variable, the partial of the second with respect to the second, and as the number of functions and variables goes higher, this matrix expands accordingly. So in this case, there's an f1 and f2, and each of them has two arguments, x and y, and so the df dx term is, we're going to give it a name, it's called a Jacobian, and that's called the Jacobian of the function. The equivalent of division is multiplication by the inverse. So we would compute this Jacobian matrix, invert it, and that gives us the 1 over df dx term that we need. Doing that and renaming our function j of x for Jacobian of x, our Newton's method in higher dimensions is shown right there. xk plus 1 is equal to xk minus the inverse of the Jacobian times the value of the function evaluated at xk. And that gives us the tool we'll need to do pipeline analyses. We'll take a few more steps here because one of the things we don't want to do in practice, usually we don't want to actually invert the function. In Excel we might, it might just be easier. But if we do a little bit of arithmetic, we can have xk plus 1 minus x to k equals the negative of the Jacobian inverse times f, multiply both sides by the Jacobian, and finally we have the negative of the Jacobian times xk plus 1 minus xk, the change in x, equals f of x. This version is much more preferable because we're not inverting a matrix. We compute a Jacobian, we treat f of x as the right-hand side, and then we solve for the unknown vector, which represents the change in x, xk plus 1 minus x sub k. We add xk to that vector, and we get the new value, k plus 1. So now we have an algorithm. Make an initial guess, compute the function, compute the Jacobian. Test if we should stop. If we're already at a stop, there's no point in continuing. Solve the linear system. Jacobian times xk plus 1 minus x sub k equals f. Determine if the change is close to 0. If not, compute the update as xk plus 1 equals xk minus the value we just computed. Move the update to the guess vector and repeat. So now using our example, in this case we'll use an analytical Jacobian, and there's the algorithm to do it, and mostly what we're going to do is we're going to build our pipeline system in order to take advantage of this equation, 59. So let's use this as an example. As I'm talking, I'm going to go ahead and sketch a copy. And so the one on the left is going to be called A, reservoir A, reservoir B, and reservoir C. The head in each of them will be head A, B, and C. It'll be QAD, QBD, QDC. That will be junction D. And we're going to follow our rules that I just outlined. And we'll use these numerical values here when we get around to it to come up with a solution algorithm. And once you can do it for one, you can do it for any system. And I'm now copying just down the pipe lengths. Okay, so there's my system, or there's my thing I want to solve. Now I want to write continuity for node D. So what do I have at node D? Notice I've assumed flow directions. That's important because it keeps track of which way flow is going. And we'll deal with the squared term in a second. I have QAD plus QBD minus QDC equals 0. Let me write the head loss in AD is equal to 8F LAD QAD QAD over pi squared G D of AD to the 5th power. Head loss in BD, same structure. Notice the absolute value here. I'm using that so that this computed sign of Q keeps track of flow direction. If we get a negative result, that means that the assumed direction and the required direction are opposite, but otherwise the numerical value is correct. Head loss in DC is 8FL DC QDC, absolute QDC QDC over pi squared G D DC to the 5th power. Those are my head loss terms for the pipe losses. So now we're just going to write the energy equation from reservoir A to reservoir D. So let's write that. We have HA minus HAD equals total head at D. Let me manipulate that a bit. I'm going to have minus HAD minus HD equals minus HA. Let's look at BD. Let's start HB minus HBD equals HD. I'll manipulate that a bit. Minus HBD minus HD equals minus H sub B. And last one, I'm going to take H at D. Notice the flow directions are dictating how I write from beginning to end. Minus HDC equals HC. So this next equation I'm going to write for the AD branch. What do I have? I have a minus HAD. I'm going to write it there on purpose. Minus HD equals minus HA. We put these zeros in here to keep everything in line. Minus HBD minus HD equals minus B, and lastly, minus HDC plus HD, slight sign change there, equals H sub C. Now those are my 4 equations and 4 unknowns, and you would think, wait a minute, those are 6 unknowns, but no. HAD, it depends on QAD. HBD depends on QBD, and HDC depends on QDC. So we'll take advantage of that observation. And let's replace these H's with the following structure. I want to take this part of an equation, or of a constant, and I'm going to call that script L. And we'll go ahead and make it a function of QDC. So now let's look what my system of equations looks like when I do that. I have QAD plus QBD minus QDC, 0 equals 0. I have minus script L, QAD times QAD, 0 plus 0 minus HD equals minus HA, 0 minus script L, QBD, 0 minus HD equals minus HB. And last one, I have minus script L, QDC plus HD equals HC. Okay, same analysis. I just haven't put numbers in yet. We're actually going to save those way to the end. Well, I notice here I have a QAD, QBD, QDC, same in these equations. I can factor those out. I also can factor out the HD, and my system looks like this. I have 1, 1, minus 1, 0, minus L. Let me drop the QAD. I'm just going to call it AD. 0, 0, minus 1, 0 minus LBD, 0 minus 1, 0, 0 minus LDC plus 1 equals 0 minus HA minus HB plus HC. And I have to multiply, use that matrix to multiply by QAD, QBD, QDC, HD. Get that right-hand side figured out. And that's now, my same system is up here, converted into a vector matrix representation. Okay, remember what I'm after. This is going to be my x vector. This is a right-hand side vector. This is a coefficient matrix. Let's call it A. Of x, because the x vector is incorporated in these script L terms. And we want to find a function f of x equals 0, and we're going to solve for x by Newton's method. Well, my function in this case is f of x is equal to a of x times x minus b. So at the correct value of x, at the correct QA, QBD, QDC, HD, that should equal 0. So with that, I now know from my prior example that I need to get a Jacobian I have a way of evaluating that. Once I put in a value for x, I can evaluate the script L's, I can perform the indicator multiplication, I can subtract off the right-hand side. So I can get f of x anytime I have an x. I now need to know what the Jacobian is. So let's go look at a definition of a Jacobian. And it says it's the partial derivative of each row with respect to each of the variables. Cool. So let me just make a note to myself. The Jacobian of x, I'm writing this, is df1, dx1, df2, df1, dx2, dot, 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 df2, dx1, df2, dx2, dot, dot, dot. So let me go back to my overhead. So I just wrote that. So let's try to find the Jacobian of my equation. And I can do anything else I can't find. More paper. Sweet. Okay. We actually may want to look at it in its original form. Okay, so the Jacobian of the first equation. So let's look at this first equation. The first derivative of that equation with respect to AD is 1. Everything else is 0. So let me get my Jacobian set up for the first one. Okay, so first equation with respect to QAD is a 1. First equation with respect to the second variable, QBD, is a 1. First equation with respect to the third variable is a -1. And the first derivative of the first equation with respect to the fourth variable is 0. And if we look at this, it makes sense. So df of this thing with respect to dqbd equals, the only thing that's left is the constant. And the same thing with here, except the constant happens to be a 0. All right, let's look at the second equation. The second equation is going to take a little bit more ingenuity, because the second equation has a constant in it. We'll just look at any one of them. We'll look at the HAD or the minus LAD term. Okay, so what does minus LAD look like? It looks like minus 8F length of AD, absolute value of flow AD, divided by pi squared G d AD to the 5th power. That's what the coefficient looks like. And it's multiplied by QAD. It's multiplied by QAD. And so now we want to find out what is the first derivative of that thing with respect to AD. Well, it's the same thing as what is the first derivative of x squared. It becomes 2x dx. So this one is going to become minus 2 times 8 FLAD, absolute value of QAD, over pi squared G dAD to the 5th power. And then dQAD with respect to itself is 1. So these terms take on the property that they're going to become minus 2 of what they were. So let's go ahead and write those in. So this one's going to become minus 2 LAD 0, 0, and then finally the second row with respect to HD is going to be minus 1. This will be 0 minus 2 LBD 0 minus 1. This will be 0, 0 minus 2 LDC plus 1. And that is my Jacobian of the matrix A for any particular x. And bear in mind that these L's depend on the value of x, so the Jacobian will change from term to term to term. Well, that finally gives me what I need, which is xk plus 1 is a vector is equal to xk minus, let me write the correct one, delete that. I want minus the Jacobian of x, evaluated at whatever xk is, times xk plus 1 minus xk equals f of x at xk. And that now gives me the ability to find a solution to my problem that will recover the flows as well as the heads at node D. So for any value of xk, this right-hand side is known. For any value of xk, we now have the ability to calculate its Jacobian, and this is a linear system which we can solve by a variety of methods. The way we're going to do it in Excel is terribly inefficient, but it'll work. Other tools such as R or MATLAB have much more efficient ways to make the solutions, and I suppose I should have everything here that I was just writing about. So this is my update. So now I need to write some sort of computational tool that easily and essentially automatically computes my Jacobian, easily and essentially automatically computes my right-hand side, and easily and automatically computes my update, and then I can recover xk plus 1 equals x sub k minus xk plus 1 minus xk. And that is what comes out of the solver. Okay, so what we're going to do now is complete this video, and then I'm going to move to a spreadsheet program, and I'm going to start to build a spreadsheet to solve this particular problem, and then you will see how it's pretty adaptable to any other small pipeline problem you can have.